Before we performing an analytical experiment, one of the most important things is to ensure the laboratory glassware are completely clean. In analytical chemistry, even a small amount of residue that are left from the previous experiment can contaminate a sample and also affect the precision and accuracy of the result. For example, the trace of grease, detergents, metal ions, or even organic compounds may interfere with a chemical reaction or analytical measurement. Although soap and water are very suitable for everyday cleaning, but they are not good enough to remove the stubborn contaminants in the laboratory. Therefore, heavy-duty cleaning such as detergent, acid, alkalis, and organic compound are used to ensure the glassware is free from the contamination and ready for analytical analysis.
Now that we understand why atomic cleanliness matters, let's dive into the core chemical theory and its industrial applications. In industrial manufacturing and quality control laboratories, simple soap completely fails to strip away stubborn, insoluble compounds like silicone grease or heavy metal residues. To solve this, we must apply advanced chemical digestion strategies. The first heavy-duty applications we frequently see in analytical setups is the use of aqua regia. This is a highly corrosive mixture formulated by combining concentrated nitric acid and hydrochloric acid in a 1:3 molar ratio. The chemical theory here relies on a powerful synergistic effect. Nitric acid acts as a potent oxidizing agent, while the chloride ions from the hydrochloric acids coordinates with metal contaminants, forming soluble chlorocomplexes that easily wash away, leaving the glass surface completely free of trace metal artifacts. Conversely, when dealing with stubborn organic polymers or specialized machinery greases, we utilize an alkaline base bath composed of potassium hydroxide dissolved in isopropyl alcohol. The underlying chemical mechanism here is alkaline hydrolysis or saponification. The strong hydroxide ions attack the ester bonds within the organic greases, converting insoluble fats into water-soluble soaps and glycerol. This allows the contaminants to detach effortlessly from the silica walls of our glassware. By understanding these specific chemical pathways, industrial analysts can selectively target contaminants without degrading the underlying volumetric glass instruments.
So now, let's take a look at a proper procedure for cleaning analytical glassware. First of all, the glassware is immediately rinsed to prevent the chemical from sticking or drying to the surface. It is then washed with elaborate detergent to remove the grease and general contaminants. If the stubborn residue is still remain, a suitable heavy duty should be selected. Acidic solutions such as dilute nitric acid are commonly used to remove metal ions, while sodium hydroxide solution can help remove the fats and protein residue. And organic solvents like acetone or ethanol can be used to dissolve non-polar organic compounds. After the cleaning glassware, the glassware must be rinsed thoroughly with tap water, followed by distilled water to remove any remaining cleaning chemicals. Finally, the glassware is allowed to air dry or put it in the oven before use. Following these steps helps to maintain the quality of analytical results and also extends the lifespan of laboratory equipment.
As we just saw in the methodology, these heavy-duty cleaning formulations are exceptionally powerful. However, with great chemical strength comes severe operational risk. Because this presentation focuses heavily on chemical safety within analytical applications, we must address the non-negotiable risk mitigation protocols required when dealing with these solutions. First, let's talk about engineering controls. When preparing or utilizing solutions like aqua regia, the reaction is highly exothermic and releases dense, choking toxic gases, including nitrogen dioxide and chlorine gas. Because of this, these solutions can never be handled on an open bench. They must be manipulated strictly inside a certified, fully operational fume hood, with the sash kept at its lowest safe working height to protect the analyst from inhalation hazards. Secondly, standard laboratory PPE is completely insufficient here. Thin nitrile glove offer zero breakthrough time protection against aggressively acids or strong base buff. Analysts must step up their digital safety literacy by consulting safety datasheets, which dictate the mandatory use of thick, chemical-resistant neoprene or butyl rubber glove, a full coverage splash face shield, and a heavy-duty chemical apron over standard lab coats. Finally, environmental stewardship is critical in analytical chemistry. These solutions can never be poured down the laboratory sinks. They must be carefully cooled, slowly neutralized to a safe pH, and segregated the designated hazardous chemical waste containers.
So here's some example of how improper cleaning can affect the analytical results. Imagine a burette that's still containing a small amount of sodium hydroxide from a previous experiment. It is later used for acid-base titration. Without a proper cleaning, the remaining sodium hydroxide will react with the acid, causing the measurement concentration to the inaccurate and leading to the incorrect endpoint. Similar in the trace of metal ion analysis, residual metal ions left on a glassware can contaminate the sample and also produce wrong result. These examples show that the clean glassware is very essential for obtaining accurate, precise, and reproducible analytical data. Proper cleaning is therefore an important part of quality assurance in every laboratory.
To wrap up our presentations, it is clear that analytical precision in basic analytical chemistry starts long before a sample is measured. It begins with the atomic cleanliness of the glassware. When regular soap and water fail to remove stubborn industrial or laboratory residues, understanding the chemical theory behind heavy-duty solutions like aqua regia or base buff allows us to successfully eliminate systematic errors. Ultimately, this real-world application from this topic prove that achieving reliable analytical data relies entirely on a delicate balance, balancing aggressive chemical applications with strict safety protocols, proper engineering controls, and responsible waste disposal. When we respect the chemistry of the cleanup phase, we protect both the analyst and the integrity of the data.